What if, when the universe slowly changes, the particles underneath do not march in steps with it at all but drift in their own staggered rhythms instead? In the energy filament theory, the universe is an energy sea whose tightness, or tension, deciding how easy it is for different filament structures to live there. But that does not mean everything scales up and down together like an image smoothly zooming on a screen. Think of a gust of wind crossing a landscape. The same wind bends big trees a little, flattens the grass completely, barely ruffles a small pond, and makes a line of wind chimes ring like crazy. One wound, many very different reactions. Because trees, grass, water, and chimes have different shapes and ways to move. A change in cosmic tension is like that gust, and the particles are like those different objects. Each kind of particle is a different knot or loop in the sea. Some are more like cleaning rings, some like twisted ropes, some like short braided segments, some like tiny built-in metronomes that tap out their own beats. When the tension wind passes over them, they do not respond together. Some react first and strongest, others respond later, some barely move at all, and some only care about changes coming from certain directions. On that spectrum, electrons are usually the most sensitive. Their filament rings are among the lightest, loosest, and most responsive structures. So, if the universe is a giant stage, electrons sat in the front row as the drummers who heard every tiny tempo change first. If it is a field, they are the finest blades of grass that start swaying at the smallest breeze. Even a minuscule change in tension nudges their internal circulation rhythm by absurdly small amounts that humans cannot feel directly, but that precision instruments can track. This is why atomic clocks work so well as environmental probes, moving the same design of clocks from sea level to a mountain, or into orbit on a satellite. And you are simply placing your electron metronomes into slightly different tension zones of the energy sea. Their timing shifts just enough that your readout moves. Electrons, though, are not the only wind listeners. Other particle properties, such as effective size, magnetic strength, spin behavior, and lifetime before decay, also respond to tension with tiny adjustments. But they are slower and duller to react. More like facial muscles that change expression gradually. When a person is surprised, their eyebrows move first, the corners of the mouth follow, and the body posture adjusts last. In the same spirit, when tension changes, the universe does not rescale like a perfect poster. It starts with the most sensitive eyebrows of the particle zoo and spreads the adjustment outward in time and across properties. That means that when the universe's tension changes, the world does not change as one synchronized block. It changes quietly, unevenly, and out of sync across different particle types and attributes. If you want to find traces of particle evolution in real data, you should not only look for global stretching or shrinking, you should hunt for small mismatches where some particle properties inside the same apparatus have already shifted slightly, while others are still lagging behind. These differences will not explode everyday life or turn water into metal overnight. They hide deep in high-precision experiments as tiny, stubborn deviations that refuse to vanish. Atomic clock drift is the first such deviation we learn to respect. It tells us that electron rhythms listen to their environment and our time readings obediently follow. In the coming episodes, we will walk this path further and look for other small moves in particles around us that mainstream practice has often been treated as noise or systematic error, but that, in the language of tension, might be little notes the universe has been quietly handing us. Those notes include the proton radius puzzle, where the same proton seems to have different measured sizes, the neutron lifetime anomaly, where different methods never quite agree on how long a neutron lives, the tiny excess in the electron's magnetic moment compared with theory, and the delicate spectral lines that seem to shift off keys by just a hair. Next episode, we'll start with the first of these notes, the proton radius puzzle, and see what it could be whispering. Tap follow, share it on New Physics, Clear Universe.